extremely early.
It'd be good to chat at some point. There's so much going on. Doing this.
I say until the end?
Yeah.
Let's try to find time.
That'd be great.
Nice.
Yeah, I heard about this in March. This segment, and I loved it. And then I got sucked by cosmic. But I'm really interested in the intersection.
Yeah, me too. Yeah, I have an idea for what so this transformers learn short tracks to autonomy.
Yeah.
So this actually is the last intersection. There are some questions on the emergence paper as well. I find it very fascinating. I kind of want to know where the art is.
Okay.
Let's talk with they both kind of wanted to watch something.
All right, shall we start?
Yes.
Thanks for coming very early in the morning to do some hard maths. And after a few days of hard conference too. So thank you. So I have I have made SLT 101 to 103 for not a good reason, but but the discussion has been great with you, so hopefully that continues. This is a summary from last time. So we set up some notation. Let's quickly recall for people who may not have been here. We set up some notation. We explain what we meant when we say geometry of a statistical model. And we will talk about that a lot more today. We defined what we meant by singular versus regular models. So in regular model, we can define the thing that we call Fisher information matrix. And in regular model, if you just expand the differences as you move in parameter space, your distribution change. How fast that change is captured by this quantity, Fisher information matrix. But then in singular model, that rate can be 0, at least in some direction. And 0 doesn't mean that it doesn't change. It might change to higher order. So we need singular models for that. So singular models are just models where the Fisher information matrix might be a singular matrix in the sense of not invariable determinant equal to 0. We'll introduce the local the learning coefficient. Crucially, I never got to the local part. The learning coefficient is related to how to quantify this degenerate part aside from just not counting things. We introduced the free energy formula. We gave a proof sketch that was a bit half complete. So let's recap that proof sketch. Right? Okay. So the free energy formula. Remember, the free energy is this. I should have just written out the free energy formula. So the free. Ooh. I want to put this on the floor. So remember, the free energy formula is n ln of W0. So that's the part that we are going to be normalized out. Where W0 is in this set of optimal parameter. Right, it's the minimum of the population loss plus lambda log n plus, I'm just going to say low order term that we won't talk about too much. Alright, so I claim that to study the free energy formula, you kind of have to trust me that we can replace the stochastic quantity, the stochastic version of things here. Remember this is the loss, which depends on data, with the population loss, and the fluctuation away from the mean can be bounded. And Simon gave a talk over giving an overview of how that factors in yesterday as well. Right. So we're going to be studying this integral, and this is just a constant up the front, and that just corresponds to that term. So this is the main object that we're going to study. Right. So, and I gave an argument last time that why we only care about the region. So we only care about the region where this exponent is less than some epsilon. Why? Because as n becomes really, really large, anything that is larger than the minimum, here we have just we have normalized things, so the minimum is 0. Anything that has like non-zero, think about this as like energy, will be exponentially suppressed. Okay, but you can just like integrate over a 0 region. What region do you care about? It is roughly of the order of like 1 on the amount of data that you have. Okay, so now we have turned this into a geometrical problem, which is looking at this sub-level set. So I should define this sub-level set. So W, I've been using T, I guess. W sub T is equal to the set of parameter in the parameter space such that the water level or the energy is less than the specified level set value T. Okay, the volume of the set is the measure of this set according to the prior, so you integrate it over the prior if you, but only in the region where this relationship is satisfied. Right, let's look at 1D picture. So if you, this is W, this is K of W. If it is x to the, if it is x squared, but that would look like that. If it is x to the 4, it will be flatter, and this water level T is like that, and you can see that that one has less volume here than the corresponding volume for x to the 4. Okay. Okay, I will define the corresponding quote-unquote area of the level set, which is you can think of I guess a 2D picture would be better. So y is better, so something like that. Right. So as this is the at t equal to something, and this is at t equal to something less. As you go down, you eventually become this is the t equal to 0 level set, right? And this derivative, so at t equal that was the area. Okay, let's just look at that quadrant. That was the area, and at t equal to t minus delta t, that this is the area. So the rate of change of the water level is related to kind of the area of the level set at that t. Right, but there is kind of a normalizing constant which is related to the
area of the level set.
Sorry.
You don't mean the area of the level set. It's like you don't mean it.
Yeah, I do mean the area. So like I do mean the area in the n Lebesgue measure in d minus 1. I'm talking about the Galvin-Leroy form.
Okay.
Yeah. so that is related to you need to account for the Jacobian of of the function, and this c here is any it can be evaluated at any point in the set. If the reference is that this is I'm talking of the Galfand-Leroy form.
It's Leray.
Sorry.
It's an A. It should be
Leray.
R-A.
Leray form.
Leray.
Sorry. R-A-Y. Sorry. Okay. So if you look at the grade book, Watanabe's 2009 book, this and the formulation in physics is this is also known as the density of states, which is the roughly the number of states at with energy T. So it can be represented as a distribution, as a Strauss distribution, right? It is equal to, well, the integral over W, but like only delta supported at that level set. Okay, so this should clearly diverge at any critical point. So if T passes through a critical value, I should say, then this quantity should diverge. I mean, that is 0 at critical points. And this rate of divergence is related to the learning coefficient, right? Oh, okay, you know that. I will. Okay. So here's a illustration. So this is x squared y squared. So that's the 3D plot of that. Okay, so I'm plotting e to the negative n x squared y squared at n equal to 1, 3, and 8. So at n equal to 1, so we know that at infinity everything should concentrate near the crosses, near the axes, xy axes. But at low end, like you see this like start to concentrate, right? And the volume, this volume T, the volume of this set, the volume of the set less than T. This is a relationship. So as T goes to 0, obviously the volume keeps going down. Right, but so at T equal to 0, the volume is 0. But then at T equal to 0 plus a little bit, it is sort of start to gain it. But 0 is a critical point of K by construction. It is a global minima. So there's an asymptote that. So this asymptote in the rate. So this is the density of state, which is the derivative of this function. Right.
So just to confirm, so T and N are the same, or?
No. So remember, we care about the region K of W less than or equal to less than T. Less than or equal to T, and T is of the order 1 on n. Right. So as n becomes larger and larger, we care about smaller and smaller T. Yeah. Okay. All right. So here's the bird's eye view of the proof strategy for the free energy formula. So this is just writing out. This is the density of states again. This is what we want. We want to do this integral. And yesterday I did the one-dimensional version, and you can see how that can go. But in higher dimension, that is harder. Okay, but here's the rough strategy. Okay, so you notice that z of n is equal to e to negative nt a of t, the density of states integral of that, right? So the rough idea is that you can exchange the integral of t and w, and notice that, so this is level set wise integral. So this is what we want, but we do a sort of a change of variable so that we integrate things like level sets by level set. This thing is just the value at the level set. Okay, and you notice that this is just the Laplace transform of the density of states. Okay, and you remember that we defined last time the definition of the learning coefficient is negative the largest pole of the zeta function, and that was the definition of the zeta function we gave, right? It is a complex. It is a complex function. That is a complex variable z, but notice that it is also again this k. The value of k, you can integrate that level set by level set, so it's t to the z, and you can relate that to the density of states via this integral, and you notice that that is a Maling transform. Okay, so this is two transforms with its inverse that we know how to do. And then the last step is to invoke I don't think I copy over. Nope. The last step, like last time, is to invoke the resolution of singularity. So why does that help? Because so recall what the resolution of singularity is. The resolution of singularity says that there exists a resolution map from the resolution, which is an analytic manifold, down to W, such that in every chart U from some domain into M, if you write K in that K after the resolution, in that coordinate chart, you get normal crossing form. And that's multi-index notation to mean U1 to the 2K1, U D to the 2K D. Right, so, and crucially, this resolution is a birational transform. By that we mean away from the singularities, it is an isomorphism. Is it okay to say it is diffeomorphism away from the singularity? That's right. Yeah. So we can represent the zeta function as, so treat that as a importantly the theorem resolution also tells us that the Jacobian itself is normal crossing. So our zeta function now becomes this. Yes.
I just wonder if you'd give me some like high level perspective here. Like if we're trying to figure out how this how anything is learning, even in the like this nice ideal Bayesian setting, knowing that there exists a diffeomorphism that we may have no idea how to compute or do anything, we can put it in this nice form. Like I guess it it then says, okay, we can there is some singular learning some learning coefficient. But like what is the thing we can compute that goes from that through this unknown diffeomorphism that has like practical import?
So an answer to that would be, that's right. This is a theoretical talk to just show that there exists a relationship that is interesting. Passed through the free energy formula.
Yeah.
And then yes, the question is, okay, this is just an existence, and and also in practice it is extremely hard to
Right.
to compute without structure. So if you have a special structure, you can compute this, but without that, it is extremely hard.
Yeah.
But there are other objects that sort of it elicit the same kind of. So this is trying to sort of pull apart the singularity by telling you, okay, so near this volume, this is the behavior of the function near this volume, right? There are other things that give you that, and that is kind of the remit of Simon's talk about jet scheme, and that is.
Sorry to interrupt you, but the first thing to say is that you can, of course, estimate the learning coefficient.
The first thing to say should be that, yeah.
Without knowing this at all.
Right.
Yeah.
So that I'm down with, but I'm wondering if is there anything other. So you have these integers, right, that you're going to get because you're going to say it's u1 to something and u2 to something.
Yeah.
And like, do those have kind of large scale properties that you could actually maybe measure that would sort of survive the diffeomorphism, the unknown diffeomorphism, and it would be some matrix that of correlations or something like that?
I don't think the integers themselves are even invariant under.
Got it.
By
Or any property of them or something.
Not on their own, but certainly correlation functions. Yeah, so that's a direction we're going.
Okay.
Yeah.
So you can ask for many other integrals against the posterior,
Yeah.
which would know more information about the geometry, which again, in principle, you could compute by going to the resolution, but you would then hope you could estimate from samples.
Yeah.
So this is like just the beginning, presumably, of probably the beginning of many other things you can apply the same sort of recipe to.
Thank you.
So this is very much in the theoretical part of this, the existence of things and wanting to find a way to get to them. We do need to understand like the details of these things and try to numerically actually estimate those details.
Maybe I'll just comment that the PhD student Ben Garrity, who's looking to treat some of this neural network QFT correspondence stuff, which is about correlation functions using these kinds of techniques.
Right. Okay. So this is basically the final step. So you do the integral coordinate by coordinate, and it reduces to this monomial integral, and we know how to do that. And once you do that integral, you can find out the largest pole easily. So this is kind of where the resolution singularity comes in Watanabe's proof, at least.
I mean, maybe we could say that at the level of, at least at the level of this integral with scale, like the deterministic one, the information that you really need about this zeta function is that it has a meromorphic continuation and the poles are real. And then you from this you get an asymptotic expansion of the. So then resolution singularity is one way to show that there is this meromorphic continuation for an analytic function.
Yeah.
But if for some other reason you know that there is meromorphic continuation.
Are the other poles important?
The other pole I thought will contribute to some lower order term, but we don't really know. We don't, I think individually we don't really know what they mean. Well, what's kind of more important is, I mean, this zeta. You can think of this zeta function like this as a distribution over W. And what's more important is the coefficient of the largest pole as a distribution on W supported on W0. That's kind of a geometric object that came into this renormalized posterior that I was talking about yesterday, and that's
Well, it's the most important as you go to, like, you zoom in the large end limit, right?
Yes.
And you zoom in, you're only caring about the local structure. But
Yes.
it potentially would, it's like some higher order, some correction or something. And
Yeah, the
less
correction
data.
that is about the lower the structure,
Yeah.
and that maybe give you a bit more sort of detail about nearby things.
Yeah.
Yeah. Okay. Yeah. So the resolution relationship of like how this is a meromorphic function. We covered that yesterday. I should have recapped that.
One note to make is that, I mean, we are not in practice, like if we're in, say, deep learning setting, necessarily in the very, very large N setting.
Right.
Yeah.
We don't know what setting we're in because we don't know what the correspondence between the Bayesian posterior and what SGD is
Yeah.
doing is in.
Yeah.
And it's certainly conceivable that, I mean, at low end we have some simple examples where we know that terms of lower order than log n
Yep.
do matter.
Yeah.
And so it's very conceivable that, like, in practice, when we're applying this to, say, deep learning, some of these lower order terms, I mean, they could really be significant. So it's not like we know for sure that, you know, they're lower order and therefore, like, who cares? Like, it's like a purely theoretical exercise to go investigate them. It is actually an unknown that could really be significant.
I'll show you an example of that.
Great. Thank you.
All right. So that is the bird's eye view of the proof. And if you want to know more, talk to me. All right. So there might be a sort of common objection that Simon have talked about yesterday as well, which is that the set of parameters where the determinant of the feature information matrix goes to zero, is zero, the singular parameters. Well, that is determined by one equation, right? It's determinant of that equal to zero. Well, that is a lower dimensional set and it has Lebesgue measure zero. So there might be a philosophical reason, maybe not philosophical, but it may be a sort of a deep fact of the world of why that set is important, that real data has optimal lying near that set. Right, but this is sort of related to what we have been talking about, which is like we are even in the modern large data set regime, we are not at the sort of a like very large infinite n picture where we only care about where the k function there becomes zero, which yes, so a priori that's likely to near it has a volume scaling of epsilon to the d on 2, where basically the learning coefficient is d on 2. But for we don't just care, we care about sort of the behavior as n like goes to infinity, and the volume that we care about go closer and closer to zero. The rate of change of volume that t might still passes through other critical value nearby, for example. So here's an illustration. So it is the same. It is the same x squared y squared function, except this time this is not k of xy equal to x squared y squared. I'm just saying that L of xy is equal to x squared y squared, meaning the population loss is x squared y squared. I haven't tell you where the minimum is yet, so I haven't normalized it to become k. Okay, now I'm going to tell you that minimum is at, so the true parameter is at xy, x naught, y naught equal to 0.9, 0.9. Okay, so the k function would be this minus the value at that. So k of xy is equal to x squared, y squared minus x naught squared, y naught squared. Okay, so you evaluate that, and then you plot the plot again e to the n k xy at different parts. It will concentrate at those at level set away from the crosses. I chose a kind of a bad example because even in this model, like near there, it is still singular, but like minimally singular. But it is not the cross, right? However, if you look at low n, that cross still shows up as, so at high n, sure, like it got exponentially suppressed. Like there's no probability mass near the cross. But at low n, this is two-dimensional so low means like 1, right? The for I think the cross is a saddle point. The origin is a saddle point. Still matters, right? And you can see that in the volume plot and the density of states plot as well. So there is there's a divergence at the origin, which is related to its own density, the density of state that we are talking about. But for some sort of finite resolution of things, there may be another effects nearby. Okay. Right. Okay. So this is playing the same game for some other. So this is saying that even a maxima will give you a signal in the density of states, and the rate of change of the density of states will the rate of change for the volume would change whenever you cross a critical value. This is the classic double well thing. As if your water level is just here, your volume is there, and then it starts to grow. But the rate of growing is related to the curvature of that one. But when you reach when the water level cross that critical value, suddenly the rate of change of water level is somehow about this about this well, right? And the sort of higher frequency feature here doesn't matter anymore. These are sort of toy pictures that we have in mind. We're not claiming that we know what the deep neural network landscape looks like. Yes?
So just a small question. So in your example there, why is 0.9, 0.9 the minimal?
I by fiat.
But like, you know, like 0, 0 achieves lower loss. So.
Thank you. I miss.
You miss squared it?
Yeah. Yeah.
Okay. Maybe I'm missing something.
Yeah. Sorry. Okay. That was actually plotted from a sort of regression setting, and the regression function was x squared y squared. That's a bad notation. W1 squared W2 squared x. So y equal to that, and then yeah. So there is the actual k is this square. Yeah, you're right. We'll do that. And the one that I plotted is that. Yes.
In the like graph you showed before of like the crossing thing with like different levels of concentration, is there like some similar effect of like a different scale if you're like, I guess early on, does like the sort of zoomed out crossing look different from like concentrating at the center, or does it like, or is there only like one scale there? I don't know if this question.
Don't really understand the question.
So I guess like my interpretation of what you're talking about in this well is like, if we zoom out enough, it looks like some larger well.
Yeah.
That's determined by the curvature. But if we zoom in,
Yeah.
there's like, I guess we'll be in like one of the smaller wells.
Yeah. For this potential.
Yeah.
Yes.
And I guess I was wondering if like when you have like a crossing potential,
Yeah.
are there like, is there like a similar thing of two distinct scales, or does it always kind of look like?
I think the honest answer for me is I don't know, because don't forget that here we are just talking about geometry. In real scenario, the n comes from sampling n data points, and if you if you are evaluating ln instead of l, this could change. Right, so it's a stochastic version of that. So whether or not that destroys stuff, whether or not the noise destroy, you may have the intuition that sort of like larger scale features is more robust, but I just don't know. All right, I will try to move on quickly.
So just I mean, the theory tells you something about the effect of noise for n. No, I mean,
Yeah. So the theory does
not like
give you control on the noise, but at the moment we don't have like theoretical understanding of what that would do to complex loss landscape. Okay. A word on generalization error. I think Simon talked about this yesterday as well. So this is the Bayesian predictive distribution. So in the Bayesian picture, so we talk about the model. We talk about how the posterior sort of evolve as n goes as n become large. You can use various learning method. Apply various learning algorithm with this model. Like you can do maximum likelihood estimation, or you can do SGD. In this loss landscape, but the one that we understand the most is the Bayesian picture. So if we use Bayesian, so if you want to predict the next observation by aggregating the prediction of all individual hypothesis by aggregating with weights given by the posterior, then that's the posterior Bayesian predictive distribution, and you get a generalization error. By generalization error, we mean how far is that estimated distribution from the true one, right? And that is given by is controlled by the learning coefficient as well. So in the regular case, this is d on 2. So in the singular case, this is lambda on 2, and lambda is usually quite a bit smaller than d on 2. So singular models generalize better when you concentrate near those singularities. Okay, not going to talk about proof. Okay, I will quickly go over the local picture of singular learning theory. So the learning coefficient is just a single number, but there is more to this, right? So here's a potential. It is let's call this kind of a line versus a point. So this is again the picture of the likelihood landscape. So it's e to the negative this function. Okay, the neighborhood of the line. So the line is representing the same hypothesis, the same function, and the neighborhood of the line. So the amount of things that looks like the function represented by the line is large, right? Because it's a line compared to the point, right? Okay, but that is only for like one value of k. You could have this kind of situation happening as well, where you can have the point dominating the posterior instead of the line, despite it being a lower dimensional thing. Okay, so this motivates the concept of like a local measure of degeneracy, which is where we get where we talk about local learning coefficient LLC.
Well, yeah. So the different. So the k is not the same on both.
The k is not the same in these two pictures. Yeah.
Are you?
Yes.
Just making sure I understand this right. So that's with like a flatter basin that's more like something to the fourth than something squared.
Yeah, exactly. So this is with k equal to 2. So this point is to the fourth power, and this one is only to the second power. Right. Yeah. Okay. So we instead of so this was a partition function. Before it was integrated. So this was integrated over the entire parameter space. We know that as n becomes large, it concentrates to the minimum of the population loss. Okay, we can break this sum. So if you have a set of partition or cover, W alpha is a cover of the parameter space. If the cover has some nice enough property, then it has a partition of unity. So P alpha is just a partition of unity. So this is just manifold theory, allow you to break any integration over the manifold into integration over covers of the manifold, right? Okay, then let's call this integral over subregion of the parameter space Zn for that part. So what is that? That is just the posterior mass contained within those regions. within any specified region, and the full posterior that integrates the full partition function would just be the sum over all partition. Okay. Okay. So each region here, you can apply the same argument throughout it, and attempt to do and do the you can get a free energy formula expansion for those regions, but for the minimum within those regions, right? So you will have negative log of Zn of W alpha is this is defining the free energy at the free energy of W alpha. That has expansion N L W alpha star plus lambda alpha log N plus dot dot dot. Okay? So you can apply the same thing, and then each individual terms Zn W alpha is equal to e to the negative Fn by definition. Okay, so and the full Z is equal to the sum over alpha of Zn, sum over alpha e to the negative Fn W alpha. Okay, so this is a sum of exponential terms. So this is like the if you apply the log sum apps approximation, the largest the largest negative Fn would dominate this sum. Right. However, at different n, so now we have a list of numbers that is n L alpha, L alpha and lambda alpha, right? So to minimize the free energy, you either want to minimize loss or minimize lambda, but the coefficient for them is different at different n regime. This curve could cross, so different parts of the parameter space could become dominant at different n. Okay, and this is related to this phases and phase transition phenomenon. If you have learning in singular models, meaning so this is from Watanabe's picture. So the generalization error that was had before at different n. Initially simpler simpler solution dominates. Simpler solution usually translate to more complex singularity, translate to lower lambda, right? And then as you see more and more data, you will want to fit the data more despite with the cost of using more complex solution, and that translates to simpler singularity, and that's the okay. So let me there's a issue with this picture, as we have sort of discussed before. How do we know that just looking at those two or the next order term is enough to tell you when and how the phase transition occur for different n? So
not to be picky, but the next order term isn't over 1.
Yeah. Okay.
Log.
Little of log.
Little, okay.
Yep. Didn't calculate. Don't know how. Yeah. Okay. Right. So we need empirical verification that like knowing these quantities can tell us something about learning system in some non-trivial system where we can nonetheless find this quantity to verify, right? And we look at the toy model of superposition introduced by Anthropic. So that's a kind of a small enough toy system where we can, with some tedious calculation, find out what the lambdas are. Well, the loss is just evaluate the loss, the population loss. I am not going to go through the definition of toy model. Yes.
Just to clarify, so like calculating these lambdas includes like figuring out how to do this partitioning of the landscape, right? Or
Correct. Yes.
some like it's like not necessarily
So
clear how to do that.
yeah. So this is a system where we know how to do it
Okay.
because those landscape within every partition the where is it going to concentrate? Well, the same story, right? It's going to concentrate to the minima of the loss function within that partition, right? So you need to characterize the set of minimas of your population loss, and it turns out that those minimas correspond to this nice geometrical structure. So this is a system where we know at least. Perhaps not exhaustively, but we are pretty confident that these are the set of like relevant critical points. Okay, so you just need to go to the neighborhood of that critical point, find a local coordinate, and that represent a patch around that, and then find out what lambda is in various cases. Right. So I just alluded to the fact that these pictures represent the coordinates. So it just the parameters consist of a matrix and some biases. The matrix has 6 columns in this particular case. The columns are 2-dimensional vectors. You plot those 2-dimensional vectors. They form this nice shapes at the critical point, at critical parameters. Okay. Right. So that's the zoo of critical points that we found and think are relevant. So they are there's a six-gon, hexagon and pentagon, and then many different kinds of fourgons. Trust me, they are different because of the biases. Okay. So and then we found that there are lambda terms and they form this quote-unquote phase structure. Which is kind of the plot of this term, this L loss term against the lambda complexity term. And this structure tells you how to trade off between complexity and loss at various different n, right? And yeah.
So just can you show the previous slide? So roughly speaking, you're saying you're going to the Bayesian posterior is going to start there and sort of make its way down and or the other way around.
That's not necessarily the case, right? So maybe the crossing point, like maybe these two is so close together that by the time you need to have an end that crosses that make the jump between here, you already want to jump here. So it's not
sort of the trend is
the trend should be that way. Yes. So as n becomes large, you want lower loss and
at the cost of
at a cost of higher complexity. Yeah, that's right.
Is complexity the
Complexity is lambda.
oh
Yeah, right. Lower lambda, more degenerate, less complex. Higher lambda, more complex, less degenerate. Yes.
When you calculate the learning coefficient here, how does your analytical calculation compare to what you get from SGLD sampling?
Do I have that? Maybe I don't have that. Like just these flashes that that slide. So pretty good. Actually, I have a slide later. I'll talk about that. Yeah.
Maybe go back and make one comment.
Yeah.
This is a really nice example where you can see that there is a difference between what the Bayesian posterior might do and what SGD can do. So we sort of see that there are the observed transitions in like some subset of the things that would be allowed by this principle that you should decrease the free energy. Which sort of makes sense, right? Because if you're in the landscape, there's like, there's some local constraints that are not baked into what the Bayesian posterior can see. Like, just because you, in principle, should go somewhere doesn't mean there's actually a path to go there. This is quite an interesting example for that. Yeah, that's right. That's it.
Thanks, Dan. Okay, so this is kind of a theoretical verification of this prediction, right? So this is plotting how many. So this is let's look at the theory first. So this is at different n. The axis is n, and this is proportion, theoretical proportion according to just that's kind of important. It's theoretical in just the first few terms of the expansion, right? So you know the first few terms. By the way, we also include the constant order term, which you can calculate by the weight norm.
You can calculate some contribution to it.
You can calculate some contribution to the weight norm, and the claim is that all that is relevant is difference in free energy, right? So you calculate one contribution and you hope that all other contribution cancel out. Okay, cool. So this is theoretical. As I say, yeah, we need empirical verification, right? So this is a proportion of this is the posterior volume at different n that get allocated to different different W alphas, right? And then W alphas here is defined as sort of a region around one of those polygons, which are critical points, right? And then you do MC sampling, and this is a, what is it? It's 18 dimensional model. MC sampling is still doable, I think. Like it's doable, but you need a lot of checks. And yeah, we do see like sort of, this is the phase transition. This S curve is reminiscent of it's a characteristic of a phase transition, and we do see that there.
There's a big bump at the start of theoretical that doesn't seem to be present in empirical. What's
this one?
No,
this one.
That one.
Yeah, so that's the next point I do want to say, which is this is asymptotic, right? So the smaller the n, the more terms that you need to consider for these two pictures to match up, right? So no claims down here.
All right.
Okay.
Right. So theory matches experiments more closely as n gets bigger.
Correct.
All right.
Yeah.
Why is the empirical sampling so noisy with some big error bars?
MC in 18 dimensional is hard.
And also there's like, there's lots of details, like how you classify things as these different phases.
Right.
It's like,
Yeah.
I mean, you have to cook up some notion of region, right?
Yeah.
That's not like an intrinsic thing. But
Yeah. Actually, I will show that. Yeah. So yeah.
Before that, can you go back?
Yeah.
So it seems that the error bars are growing with n.
Say that again.
The error bars seem to be growing with n in general.
At least with the two big ones.
Yeah.
These are two big ones.
Is there a reason for that, or?
Let me show you what the posterior sampling looks like, right? The colors are the different phases, colored by different polygon, and how we classify them. So at low n, you see that so from 4 gon to 5 gon to 6 gon, 6 gon is a global minimum. Even though 6 gon is a global minimum, the red thing it is not actually as well represented at 300. Like there, a lot of other things get sampled as well. A lot of other phases get sampled as well, right? As you increase in n, so in 500, 700, 1,000, red starts to get dominated. This is a TSNE projection of this posterior sample.
Yeah, I was gonna ask what the axes were.
Yeah, a TSNE projection. Yeah.
All right.
Yeah, and then you start to see the 5 gon, the two lowest energy, lowest loss states sort of start to dominate, and then finally just a 6 gon is dominating. Why does that tell us anything about the error bar? I don't really know. Yeah, I have a go here to like there is a TSNE visualization of all chains. You can look into it to your heart's content. Okay, I ran out of time. Let me just show you that that's what Dan mentioned, that this relates to the green curve is tracking the LLC, and yes, it tracks pretty closely to the theoretical LLC. Right, and at phase transition, LLC change. For these systems, like the loss obviously also change a lot. Okay, I think I ran out of time. We don't need a recap. There's a lot of things I didn't talk about. Thanks for coming. We do not have time for questions. Oh, we do actually. Like one question. Yeah.